Hello, am I audible?
Yes, sir, you're
Yes,
audible.
sir.
Yes, sir.
Okay, great. So in today's session, we'll be discussing about week 5 and week 6, and in tomorrow's session, we'll discuss about week 7 and 8. Okay. For
Okay, sir.
quiz 2, we have week 5 to 8 syllabus. So let me share my screen. Yes, any question?
Sir, PYQ discussion, sir.
PYQ, yeah. If you have any previous year question, if you have any doubt in that, you can ask us. Okay.
Okay.
But let me cover the revision part first. I will solve the mock test questions, then you can ask. So today we'll discussing week 5 and week 6. Wait. So this mock test. I hope my screen is visible, right?
Yes, sir.
So see, syllabus is basically week 5 to 8, right? But if you see, almost 70% weightage will be given to the week 5 and week 6 content, and the rest will be week 7 and 8. Okay, so very important week for the quiz 2, and even in end term point of view also, you can expect a higher weightage for week 5 and 6. Okay, so there will be a total of 14 questions and for 50 marks. Okay, this is the paper pattern for quiz 2. So in week 5, what we have discussed? We have discussed about the functional dependency concept here, right? Functional dependency concept. Now, when I say A determine B, so can anyone tell me what do you understand by A determine B?
B is functionally dependent on A.
B is dependent on A, right? So we can say that, let's say for example, here we have three columns A, B, C, and let's say we have this functional dependency A determine B here, right? If the value of A is basically A1, and here let's say B1, C1, here we have A2, B1, C2, here we have A3, let's say B2, C3, and we have A1, B2, C4. Now, is this function dependency valid for this particular table?
No, sir.
No, no, sir.
No, right? Because A uniquely determines B. Okay. So here word uniquely is very important. So A uniquely determines B. It means what? If A1 is determining B1, then A1 should determine B1 only. So you can see here A1 is determining B2, which will violate the functional dependency. So this is not correct here, right? Because of this, it will not be applicable, right? So A1 should determine B1 here. A2 determining B1, that is fine. A3 determining B2, that is also fine, right? So this left hand side value should uniquely determine this right hand side value. This is what we can say about the functional dependency concept here, right? Anyone, any doubt? We have discussed this thing in detail in week 5. Any question, any doubt based on functional dependency?
No, sir.
Okay, great. So after this, we have discussed about the closure of an attribute. Closure of attribute. So very important concept. In every question of week 6, we need to find out the key. For that, we need to find out the closure of an attribute here. Let's say, for example, I have this relation R having the attribute A, comma B, comma C, comma D, comma E. And here we have a functional dependency like this. Okay, A, comma B, C, comma D. And let's say, for example, BD, comma CE. Okay, let's say only C here, right? So we have this particular functional dependency here, right? Now, if I want to find out the closure of an A, so what will be the closure of an A?
A, B, C.
Yeah.
A,
So
B.
first, A will itself determine A, and from A you have to check the functional dependency set from which attribute we can determine. So from A we can determine B. So I will add B here. Now we have to check either from A or from B or from EB. Can we determine something here?
No, sir.
No, sir.
No. So the closure of A will be AB only. That's it, right? So in this way, we need to find out the closure here. Let's say, for example, if I say AC closure, what will be the AC closure here?
A, C, B, D.
BD.
D. BD.
Yeah,
BC.
so from AC, it will determine AC, but from A, we will get B, but from C, we will get D, and from BD, again, we are getting a C here, right? So let's say this is, okay, C, fine. So this is what we are getting here, right? This is a AC closure. I hope everyone knows how to find out the closure of any attribute or set of attribute, right? But why we are doing this? To find out the key here, right? So what's the concept of key? Yes, anyone?
If you find a closure of key, it will give a relation, interrelation.
Yeah, so
We are
what? Yes.
Uniquely determines a row.
Yeah.
we are
So
checking if any attribute is like covering all the attributes of R or not.
yeah.
Super key and candidate.
So key is basically what? It will uniquely determine that particular row. Uniquely determines row here, right? So if I know the key, I will get all the information about that particular row. For example, in a student table, we have a roll number as a key. So if I just know the roll number, I can get the entire information of a student, right? Like that. And in terms of closure, what we can say, if I take a closure of any attribute or set of attribute, and if that closure is giving me all the attributes present in the relation R, all attributes here, so that particular attribute or set of attribute will be my key here. So we can say if I take a closure of any key, that should give me all the attributes in the relation R here, right? So if you want to check whether that attribute or set of attribute is key or not, we can simply take the closure and we can find out that if we are getting all the attributes or not, right? Now we have two different types of keys based on the functional dependency. First one is candidate, second one is super key. What is candidate key? What is super key? Yes, anyone?
Candidate key is the minimal key which we can use to identify unique entities, and super key is the mixtures of those. So candidate key is the proper subset of super key.
Yes, correct. We can say like that. So candidate key is basically minimal super keys, and even candidate key is also a super key here, right? So every key is basically super key, we can say, but minimal of super key is basically a candidate key. Okay. So if I say A, B, C is basically a super key here, right? So we need to check whether A is key or B is key or C is key or any combination of A, B, B, C, A, C is key. That will be a minimal of super key, and that will be candidate key here, right? But how we used to find out the candidate key if we have a functional dependency? Yes, anyone? How to find out
With the help
candidate
of
key?
closure. With the help of closure.
We will
Yeah. So
we'll
how
try
to
to
go? So
Those
decompose this.
attributes which are not present on the left.
yes. So what we do first, we always go with this particular method. First, always try to find out the attributes which are not present, on right hand side of any functional dependency. Okay, right hand of any functional dependency. It means what? That attribute cannot be determined. Can we say like this, right? If that attribute cannot get determined, it means that must be a part of the key. This is what we can
Yes.
say, right? So tell me, for this relation and for this functional dependency, what is the key here?
A B D. Oh no no no. A B C.
A and C. No, C A only said.
Only A.
Only no. If I take the
A
closure of A, I am getting AB only, not all the attributes, right? So key should give all the attributes, right? What's the closure
A
here?
and C.
So there won't be any super key,
AC.
sir. E is missing over here, sir.
No, just apply this whatever I have written here.
AC.
No, even if you take the closure of AC, what you are going to get? A, B, C, D only, right?
Yes.
A and E.
Yes.
Oh.
So what we have said, the attribute which are not present on right hand side of any functional dependency. B is present, C is present, D is present. A and E is not present. So first we need to check whether AE is key or not. How we can check? Simply take the closure of those attributes and see here, right? So from A, I can get a B. Is this a key? I
We
guess
need to
that's
No,
it,
check
sir.
E also.
right?
It
So
will
no,
need D also or C.
It is
yeah,
not there, sir.
yeah. So what we have said, the attribute which are not present on the right hand side of any functional dependency, that must be part of key. Must be
Essential attribute.
part of key, or we can say essential attribute, right? So either that particular attributes can be a key or it will be a part of the key here. So as we know that first we need to check whether those attributes is key will form a key or not. But here we can say we are not getting all the attributes, it means A is not a key. Now in that case what we have to do, here we need to take a combination of this attribute with all the attributes here. So A with B, A with C, A with D here. Now see, after taking closure, which is basically key. What about AEB? What's the closure of AEB? AEB only, right? What about AEC?
A, B, C,
A,
D.
E, C,
DT.
D.
BD, right? So we are getting all the attributes here, right? Of R. So AEC will be a key. What about AED?
A,
Same.
E, C, D. Yeah, all.
BED.
A DC.
Yeah, we are getting C also, right?
Yes.
Yeah.
Yes.
Yes,
So
sir.
here's also R. So here we got two candidate key, right? So table relation or table can have multiple candidate key. Okay. So table can have multiple candidate key. Super key will be always a multiple here, but a primary key will be only once. Okay. So primary key is one, but candidate key can be multiple here. And out of those candidate key, we select any one of the key as my primary key here. So here we have found that our candidate keys are AEC and AED. Anyone, any doubt how to find out candidate key?
So E is even not a part of functional dependency. Still, we are including it, right?
E, right? Yes,
E.
yes. Because this attribute cannot be determined by any attribute, so
Hmm.
that must be a part of key here.
By default, it becomes like
Yeah. So because we cannot determine, right? So by default, it will be a part of the key.
so. Will it be a prime attribute or non-prime attribute, sir? How will you determine that one, sir?
Yeah. So once we find out the candidate key, now what is prime attribute and what is non-prime attribute?
AECD primate.
Yes. So attribute which are part of candidate key. Attribute which are
Part of 21.
part of candidate key is basically my prime attribute. So here we have A, E, C, and D as well, right?
Yes.
So here we have four prime attributes. What are non-prime attributes? Remaining are my non-prime attribute, that is basically B here, right? So you should know how to find out the closure. You should know how to find out the candidate key and how to find out prime attribute and non-prime attribute. Okay, these steps are very important for week 6 content. In every question, we need to do this particular thing only. Anyone, any question here?
Sir, but D is an attribute which is present in right hand side for C.
Huh?
So
Yeah,
will it be
yeah. This
a
will be a,
key?
no. D is not a key here. A, E, C, and A, E, D combination is a key, right?
Yes, sir.
Yeah. So what I said, the attribute which are not present, that must be a part of candidate key. Okay. So we have talked about which are not present. Which are present, that also be a part of candidate key. But here it must be a part of candidate key. Okay. So first, always find out the attributes which are not present on the right hand side of any functional dependency. Find out the closure. Check whether you are getting all the attributes or not. If you are not getting all the attributes, then go with the combination of the remaining attribute and then check whether we are getting the all the attributes or not after taking the closure. Okay. So this is about how to find out the key. But what if I say we have this relation R, A, B, C, D, let's say E also, and I have this particular functional dependency. A determine B, C determine D, E, and let's say B determine C here. Now in this case, what will be candidate key? Tell me.
E.
Wait, A is also not
A,
present.
B.
Wait. B also, yeah, B determines CA now. Now tell me.
Now we have to find
Okay.
closure of all combinations.
Yeah, so
B is the candidate. A and B.
we'll see, right? So here you can see, like, if we go with that particular method, right, which attributes are not present on the right hand side. So you can see A is present, B is present, C, D, all are present. It means what? We cannot apply that particular rule. Now in that case, we have to go by a traditional method, that is basically take the closure of individual attribute here. So if I take the closure of A, take the closure of B, take the closure of C, D, E, like that. So if I take the closure of A, what I'm going to get? A, B, C from C, D, E. That is basically a
All.
key. What about B?
All.
B, C, A, and A is anyway a key. So we are going to get all the attributes here, right? R. What about C closure?
Only
D.
D.
Only C, D, E.
Only C, D, E. What about D closure? Only D, E, only D, E, right?
Yes.
So here we know that A and B, after taking closure, we are getting all the attributes here. So candidate key will be A and B. But we have to check for other combination as well. We are left with C, D, E. We have just checked for the individual closure here, not the combination of those particular closure, right? So then we have to check the closure of C, D, D, E, and C, E here. So whether any, is this a key? If you take the closure of all this attribute, no. CD
No.
will give me CDE, DE will give me DE, CE will give me again CDE only, right? So then we have done with all the combinations. Anyway, CD is also not a key. So we just have two candidate key here, A and B here, right? So we have to check for other attributes along with the combination also, right? We are not checking for A, B, sorry, or A, C, D, E, because anyway A and B are my candidate key. If I take a combination of candidate key with any other attribute, that will become my super key here. Okay. So we don't want to find out super key, only candidate keys here. Okay. I hope this is clear how to find out candidate keys. Anyone, any doubt, any question? Okay. Is this clear how to find out candidate key?
Yes.
Yes,
Yes,
sir.
sir.
Okay. Then we have how to find out number of super keys. Okay. Very important concept quiz 2 point of view, even any exam point of view, right? So how to find out a number of super keys here? Let's say we have a relation R and having candidate key. Okay, let me write down the relation here. Same thing, A, B, C, D, E, five attributes we have. And let's say, for example, we have just two candidate key here, A and B. Okay, first let's say only we have A. Tell me how many number of super keys we have.
16.
16.
Okay, if we have A and B as candidate key, number of super keys, and if we
8.
have A, B, and B, C as candidate key, then how many super keys we have? So first, how to find out a number of super keys? As anyone, someone said, how many for this case?
16.
16.
16. How you got this 16?
2 to the power of number of extra attributes other than the candidate key.
Yeah, it is basically n minus m here. What is n? Total number of attributes in relation R. Okay, in R, m is basically number of attribute in candidate key. Okay, now here n is basically 5, right? What is m? How many attributes we have in candidate key? 1. That is basically to the power of 4. That is basically 16. Okay, so you can remember this particular formula, to the power n minus m, where n is basically a number of attributes in R and m is basically number of attributes in candidate key here. This simple one because we just have one key here. What about this particular case when we have two key? How to find out?
Same formula.
8.
Yeah, but here you can see candidate keys using A, that will be to the power 5 minus 1, that is 16. Candidate keys using B, we can find out to the power. Okay, how you got 8?
So the answer is 24.
Correct.
Like, we have to
Yes.
use the formula N of A
Yeah.
intersection B, N of A plus N of B minus N of A union B.
Correct. So here what we have said, this is for that particular candidate key. So using one key, how many super keys we can get? So here we have two keys, right? So using A, how many key we are getting? Super key to the power 5. We just have one attribute, that is basically 16. Number of super keys using B, how many we are getting? Same number, that is 16, right? But
Yes.
if you take a combination of A, B, C and B, A, C, so this will be in both the sets, right? Using A also, this is super key. Using B also, this is super key, right? So there are some common combination that we have to remove, right? In both the set, we have some common combinations here, right? So how we can do that? So we can use that particular formula, number of super keys using one super key A. Let's say for example here we have CK1 and CK2, right? So CK1 and CK2. So number of super keys using both the candidate keys. So let me write down the formula. We have learned this in our probability, right? So this is basically number of super keys using one, then number of super keys using second candidate key. We have to subtract number of super keys CK1 union CK2 here. Okay, so you can remember this particular formula. Now let's see, using A we have 16, using B we have 16. What about CK1 union CK2? Yes.
8.
8.
You have to use both.
Yeah, so A union B here is basically AB. So using this particular key, how many super keys we can get? To the power 5 minus M is basically 2 here because we have two attribute, that is basically 8. So minus 8 here. So that is 32 minus 8. Answer will be a 24 number of super keys here. Okay.
Sir,
So
union, I think it should be intersection, right? Because out of ABC, BAC, we are taking AB as common.
no, out of two key A and B, we are taking union of this. Okay. So A and B here. Union of that. Similarly, you can apply for this here. Okay. Now tell me in this case how many super keys we have.
12.
12.
Well,
Super key using AB. So to the power 5 minus here we have two attribute. It is 2. So 8 we got. Same for BC as well. 5 minus 2, that is basically 8. Now what about the combinations here? CK1 union CK2 is basically what? ABC, right?
4.
So using these three attribute, how many keys we are getting?
4.
4, right? So we can say that is 8 plus 8 minus 5 to the power, so to the power 5 minus 3, that is basically 4. So 8 plus 8, 16 minus 4 is basically 12. Okay. So you can see we have three different cases when we have one candidate key, two candidate key, and here we have two candidate key, but there is some common attribute, right? If there is no common attribute in the union, that will be 4 attribute. That's it. Okay. So these are the three possible cases you can expect in the exam. Let's say, for example, we have one more key. We have three keys here. In that case, we have to go for a different formula. It is N of A intersection B intersection C. So that N of A plus N of B minus N of A union B, that formula we have to go. But anyway, we are not checking your mathematical thing here. So we'll only ask up to these two candidate keys here. Okay. Anyway, any doubt how to find out number of super keys now in all the three cases? Is this clear?
Yes, sir.
Yes.
Okay, great. So we have discussed about functional dependency, closure, key, prime attribute, non-prime attribute, number of super keys here, right? So this is a basic required to solve any question for week 6, even for week 5 here. Okay, so let's try to solve any one question from the mock test based on this one. So normal form we don't want. Here also we have normal form, we'll discuss later. Yeah, okay. Anyway, you can see the answer here, but let's solve question number 7. Why this option, these two are correct? Why not A and B? How to solve this particular question? Yes, anyone? How to approach?
Check the right hand side.
Yeah, so W is present, Z is present, V is present. So XY must be a part of key here. But if I take the closure of XY here, so what we are going to get?
Only
Only
XY.
XY,
XY.
only XY. Then go with XYW, XYZ, and XYV and C, which is basically a key here. So if you take the closure, option A, sorry, option B and C will be a correct one here. So please remember here we are finding out number candidate keys, okay, not super key. Some student will do simply they will go for a closure of each and every attribute and they will find out which one is giving me all the attribute that they will mark as the answer. But that is only applicable for no, not only applicable, but we can say that will give us super key. Okay, so we have to check for a minimal of that. Even if I say here WXYV here, even if you take the closure of that, you will get all the attributes here, right? So make sure what is asked in the question. If we ask for which one of the following is super key, then the best way is take the closure of each and every option and see what you are getting. All the attributes in the relation are or not. That's it, right? But in the case of candidate key, we need to find out the candidate key here. Okay. I hope this is clear, like what I have explained about, right?
Sir, can you repeat, sir?
Yeah, so here we have asked for candidate key. So you need to find out the candidate key here. So earlier we have discussed that if we take the closure of a key here, that will give me all the attributes in the relation R. So here also same thing will happen. But what if we have one more option, WXYV here? Here also you will get all the attribute, but this is not a candidate key here. Candidate key is basically minimal super key. Okay, so this is applicable for a super key. Anyway, candidate key is also a super key here, right? Minimal super key. But if we ask for which one of the following is super key here, then simplest method is to take the closure of each and every option. That's it. Okay. But candidate key, we have to find out the attributes. Okay. Great. Yeah. So anyway, we can it's the question based on the this one. Then we have this. Okay. So we'll discuss this one. Good question. Okay. So this is what about the number of super keys we have. Then we have something called decomposition. So what is lossy and what is lossless decomposition? As anyone? Tell me what is lossy, what is lossless decomposition?
When we don't have any redundant data, then it is lossless.
Lossless when even we join results in the original table.
Yeah, correct. So let's say, for example, we are decomposing one relation into R1, R2, or let's say, for example, R3 as well. So what is a lossless decomposition here? If I join all the three decomposed relation, I should get my original relation back. Okay, no redundant data, or we can say no extra rows, right? Same number of rows, same number of columns. That's it. I should get the original relation back. That is what a lossless decomposition is, right? Lossy means what? There can be few extra rows, right? If there is lossy decomposition if we perform, and if we just perform a join operation, then we are getting some extra rows which is not present in the original table, or few rows are missing which is not present in the original table. That is basically a lossy decomposition here. Okay, so that will happen if we don't follow that particular conditions. Okay, so let's say we have R, we are decomposing into R1 and R2. So we have three conditions to ensure that our decomposition is lossless. Which are those conditions?
R1 union
Section
R2.
R2.
Yeah, R1 union R2 must be equals to R. This means what? Number of attributes, or we can say columns, we are verifying that is same or not, right? Number of attributes, number of columns, or we can say attributes, right? Let's say we have here A, B, C, D, E, and here we just have A, B, and here we just have D, E, right? But in this case, if I take union, I am not getting R, right? So this is not a lossless decomposition because one attribute is missing here. Now second one is, tell me.
R1 intersection R2
Intersection
implies
cannot be
R2
null.
Not
cannot
equals
be
to
null.
empty set here. So what do you mean by empty set here? Whatever the whatever the intersection we perform between R1 and R2, or we can say common attribute between R1 and R2, there must be some common attribute, right? So this means what? There must be some common attribute between two tables. What about the third condition here?
R1 intersection R2 must be key in either R1 or R2.
Yes. So R1 intersection R2 should give me either R1 or R2. It means what? This particular common attribute must give me either R1 or R2. So key means what? How we can check? Simply take the closure of that particular common attribute and see whether we are getting R1 or R2 or not. That's it, right? So that common attribute must be a key of either R1 or R2 here. Okay. So if we verify all these three, then we can say that our decomposition is basically a lossless, right? So yes, anyone any question here?
Sir, in this last condition, do we need to get any attribute in that relation, or else hold the relation do we need to get if we take a closure of R1 intersection R2?
Okay, so let's say for example here we have C. Okay, so here we don't have any intersection. Let's say here we have C as well. Now C is common, right, in A, B, C and R2, R1 and R2. Now if I take a closure of C here, I should get either R1 or R2 here, either A, B, C or C, D, E. Okay.
Yes, thank you.
Yeah.
Means
So
there should be a dependency among.
yeah, there should be a dependency from which we can determine any one of the relation here. Okay. It's about a lossless decomposition here. So I think we have one question in mock test. Yes. Okay. Yeah. So here you can see we have the relation, we have the functional dependency here, right? And then which of one of the following is lossless decomposition here. So what to do? How to check for option number one here? We have three decompose relation. How to check in this particular case?
Union. Yes.
Yeah.
First, we will take union.
So see, whatever we have discussed here, right? These three things we apply while decomposing the relation, right? But here we need to check which one, like for decomposition is lossy or lossless or not. So in this case, what we will do, first we'll check whether R1 union, R2 union, R3 or whatever decomposition we have till Rn must give us R here, right? This is the first thing. Then second, we have to take any two decomposition such that there is some common attribute between them. So you have to check you have to take those relation and check whether we can join those two table or not. Okay, so how we can do that? First, check for this particular first condition for the first option, is this satisfying? Are we getting all the attributes here after doing union of all the three?
Yes.
Yes, sir.
A, B, C, then we have I, J, D, E, F, G, H is remaining. Yeah, this is covered. Now, from these three relation, take any two which is having common attribute here. So which relation having common attribute?
R1, R3.
R1, R3.
R1 and R3 here. So R1 intersection R3, right? What is that?
I.
I. Yeah. So is I is basically key of R1 or R3. We need to check that. Simply take the closure of I and check whether we are getting R1 or R3.
Nothing, we are getting nothing.
Nothing. Only
I only, right? It means what? I cannot join this R1 and R3. Okay. Can we check R1, R2, but no common? R3, R2, there is no common attribute. It means what? This is basically a lossy decomposition. Okay. If I join this three relation back, I will get some extra rows into the table. That is not equal to original table here, right? That is basically lossy decomposition here, right? Anyone, any doubt what we have discussed? Why option A is not correct? What about option number B? Check for first condition.
Yeah, it's true.
Now take any two decomposed relations such that there is some common attribute.
R2,
R2,
R4.
R4.
R1, R2 we cannot take no common attribute. R1,
R2,
R3, R1, R4 we can no R1, R4.
R2, R4.
R2, R4.
R2, R4, right? R2, R4 only, right? So if I take R2 intersection R4, so what is the common attribute here? We have D. Is D is basically a key of either R2 or R4.
R4.
So if I take from Dij, I am going to get Dij, which is basically my R4. It means what? I can join this two table. Okay, so I can join R2 and R4. Let's say I perform a join, and resultant table will be R24, such as R2 union R4. Now, once you find out, okay, we can join those decomposed relation. What we can do, we will say, okay, R24 is basically R2 union R4 because we can join this relation. So we'll get the attributes as D, E, F, I, J in the output, right? Now we have R24 and R1 and R3. So out of these three, which table we can join?
None.
Nothing
No.
in common.
So we cannot join because there is no common attribute. If there is no common attribute, in that case, it will perform cross join. So we are going to get more rows. That is basically a lossy decomposition again, right? So option B is not correct. What about option number C? Yes.
So, sir, for the second condition, we should check the common attribute between every relation.
Yeah, so first take any two relation. Okay, so here we have taken R2 and R4 because we can see common. It means what? If we are getting R2 or R4, it means we can join these two relations. So we have joined that relation and say resultant will be R24. Now I left with R1 and R3. So can I join R1, R3 or R24? Because there must be some common attribute. No here. So it means what? We cannot get the original table here. So this is like that. So here we have R1, here we have R2, here we have R3, and here we have R4. Lossless means what? If I join all the four, I will get my original relation back. So first I will try to join these two relation. I am getting R24. Now I need to join R1, R3 or R24, but I cannot perform the join operation because there is no common attribute. So in that case, we will get a lossy decomposition here. Now you can see option number C here, right? So first, anyway, it is correct. A union R1 union R2, R3, R4 is giving me all the attribute. Now tell me which attribute or which relation we have to take. Which two relation which having common attribute?
R1 and R2.
We can take R1, R2. We can take R3, R4. We can take R5, R2 as well. Anything, right? So let's go with R1, R2 here. R1 intersection R2. So that is basically A in common. Whether A is key of either R1 or R2.
R2.
Yes, sir.
So you can see here ADE. ADE. That is basically R2. It means what? I can join this relation. So let's say, for example, say R12 is basically what? R1 union R2. That is basically A, B, C, D, E. Now I have joined this two table. Now we have R12. Now we need to check whether we can join R3, R4, R5 with R12. Okay. So we can go in any combination, either R12 with R3 or R5, or first we join R3, R5, then take R3, 5 with R12. It depends, right? So let's go with R12 intersection R3 because we have B in common. Is this? Can we join this two tables now?
Yes, sir.
Yes, sir.
Yes,
Because
sir.
common attribute is basically what? B here. And if I take the closure of B, what I'm going to get?
BF.
BF. That is
R3.
basically R3. It means what? We can join
R12 with R3.
Hello, sir, you are not audible.
Yes, sir. You are not audible.
Sorry, there's a power cut here. Just a minute. Okay, great. I hope I'm audible properly, right?
Yes, sir.
Yes.
Yes, sir.
Okay, so yeah, so here we can join R12 with R3 because of
Sir, your
Screen,
screen is
Your
screen
screen
is
is
not
not
visible.
visible, sir.
not visible.
Yes, now it's visible.
now it's visible.
Okay, fine. So if I take the closure of B, what I'm going to get BF, which is basically R3. It means what I can join R12 with R3. Now let's say, for example, say R123 is R12 union R3. That is basically what A, B, C, D, E, and here F, right? So here we have R123. We are left with R4, R5. Now can we join R123 with R4 or R5?
Yes, sir. With
R4.
R4.
So let's go with R4 here, right? Or R5. Anyway we can go. So let's go with R4 only. So here R123 intersection R4 is basically what? F, right? From F, are we getting R123 or R4?
Yes, sir.
R4.
R4, right? So we can join R123 4, that is basically A, B, C, D, E, F, G, H. And again, if you take intersection of A, B, C, D, E, F, G, H with R5, So that is basically D in common, right? So that is basically, let me write it down here. A, B, C, D, E, F, G, H. Now we left with 5 only, intersection R5, that is basically D. And if I take the closure of D, I am getting R5 here, right? It means what? I can join this resultant table with R5 to get the original relation back. So option number C is correct here. Okay. Anyone, any doubt here? How to check whether the decomposition is lossy or lossless? Now, can anyone tell me why option D is not correct? Which table we cannot join here? What about option number D? Why it is not correct?
R1 and R2. R1 and R2.
R1 and R2.
R1, R2, right?
The common attribute D only determines I and J.
Yeah. So first we can check for R3, R4 also. Now, if I go for R3, R4, I can join this R3, R4 because of B is common. B is giving me R3, so I can join R3, R4, right? Now I can go with R2, R5. I can join R2, R5 as well. That is R2, 5 is basically D, I, J, E, right? R3, 4 is basically B, F, G, H. Now we are left with R1, A, B, D. Now try with R1 and R5, that is basically
Yes.
D in common, but from D I am going to get Dij only. I will not get E here, right? So
Yes, sir.
it means what? I cannot join R1 with R25, even R1 with R34. Because of this, we can say it's a lossy decomposition, right? It's not like that if you just take any two a decompose relation and here we are checking if we cannot join. No, check for other combination as well here. Okay. Okay, great. So this is how you can proceed for. Yes.
Excuse me, sir. Sir, when we are looking for the common attribute by intersecting two sets, at that time, whatever attribute we got, we are checking whether the complete set of attribute is determined or not. Is it like that?
Yeah. So either that particular relation R34 or R25 in that case, any one of the relation should get determined.
Okay.
Yeah.
Thank you, sir.
Okay. So this is about a lossless decomposition here. Now then we have one more concept of dependency preserving. Okay. Now what is the dependency preservation here? Question based on this? No. Okay. So let's say, for example, I have decomposed this relation only. Let's take this only R1 with this one, right? A, B, C, D, E here. So here we have R. So how to check for dependency preserving? First, write down all the decomposed relation and its applicable functional dependencies, right? So R4, and then we have, how many we have? R5. R5, it's Dij. Here is basically is D comma F. Here is basically what? FGH FGH. Here we have ADE. Here we have ABC. Okay. So you can see we have write down the decomposed relation. Now write down whatever the functional dependence is applicable to this R1, that is basically F1, for R2, F2, for R3, F3, for R4, F4, and for R5, F5. Okay. How we can write it down? So for R1, which functional dependence is applicable here? Can you check?
AB to C.
Any other functional dependency here?
No, sir.
So you can see it AB determines C. So all the attributes are present in R1. So we can directly say AB determines C is applicable to this R1 here. We can write it down in F1, right? What about R2, A, D, E?
So A gives D.
A to D, E.
A to D you can see here, right? I cannot write AD in F1 because only A is present. D and E is not present. I have to write it down in this F2. Then we have B determine F here. Okay, for R3, I guess BF, right? Then we have DIJ and FGH. Okay, I guess here for individual thing we have this one. Okay, so you can see here all the functional dependencies which is in the parent functional dependencies is now applicable to all the relations here. So we can say this decomposition basically is what? Dependency preserving, right? But what if, let's say for example, I am saying A, B, C, and here we have F, G. A determines, no, not A. What is the key here? F, G, H, A, B, C. Hmm. B, F, G, H. Okay, so B determine H here. Okay, so we will add one functional dependency. Okay, like what we have done. Any question here? We have just write it down the relation decomposition and its applicable functional dependencies from the parent set here. Any doubt here? Okay, great. So you can see all functional dependencies is applicable to any decomposed relation. So we can say dependency is preserving. Now let's say for example, I'm adding one more dependency here, B determine H. Now tell me where this B determine H will go, in which decomposed relation? Yes.
Nowhere.
Nowhere, right? So can we say that it's not a dependency preserving? So first write it down all the applicable functional dependencies like that. Now the dependencies which are not applicable to any decomposed relation, for this particular case we have this particular functional dependencies. For this FD we need to check whether this is applicable to any one of this or not, or preserved or not. Okay, so we have to check whether this functional dependency is preserved or not, because remaining functional dependency is already preserved in respective relations here. We cannot add BH in any one of this because B and H is not present in single relation here. So how we can check? Now tell me the method how to check for dependency preserving.
By combining two different rows.
Or taking the closure and if it's giving all the functional dependencies.
So this is F1, F2 is basically what? All applicable functional dependency to R1. Applicable FDs to R1 here, right? So here AB determines C is fine. We can directly write it down. But can we write A determine BC? Can we write B determine AC? Can we write AC determine B? Any one of this here? Because these things are possible, right? So how we can check which one is applicable here? So we need to write down all the applicable. That is what F plus here. Okay, F plus here, all the applicable functional dependencies. So for that again you need to go take an individual closure here. If I take a closure of A, I am going to get A, D, E. So B and C is not present. If I take B, B, F, from F we have G, H, but C and A is not present. From C, no. So I cannot determine anything from A, B, C except this one. I will not get any functional dependency, right? What about F2? Here we have written A determine DE. Can I write D determine A or E determine AD like that? So how we can do that? Simply take the closure of those attribute based on the parent functional dependency here. Okay. So I know that A can determine DE, but can D determine A? Can E determine A? Or can E determine AD? Right? Because that will be applicable here. So that we have to check. So if you take the closure of D and E, because if I take a closure of A, anyway, all attributes are getting covered. So I left with DE only. So if I take a closure of DE, if I take a closure of D, what I'm going to get? DIG only.
DIG.
That's it. E only. So no. And DE only. So that's it. No functional dependencies here. What about BF? So here we can say B determine F, but can I say F determine B? We have to check for this as well. Can we say F determine B? No. That's it. Right? F determine GH? No. What about F determine GH? Can we write G determine HF or G determine H here like that? So go for G closure and H closure here. If I go for G and H closure, what I'm going to get? GH, nothing, GH
GH
only.
itself.
Yeah, so again, we cannot derive any functional dependency. What about F5? So we have D, I, J, but what about I and J? Can we get any other FDs here from I closure or J closure? No, right?
No.
So this is the only applicable functional dependencies we have. So once we find out F1, F2, F3, F4, F5, what we need to do? We need to find out F dash such that F1 plus union F2 plus union F3 plus union F4 plus union F5 plus, right? And then check whether we are getting this particular functional dependencies here after taking union of this one. So are we getting the B determine H here if I take a union of all this one?
Yes.
Yes. So if I take,
B determines F.
yeah,
F
if I
determines
take
H.
this two thing here, so here we have B determine F and F determine GH. If I simply apply transitivity, or even if I take a closure of B here, because we are checking for this. So simply take the left hand side closure and see whether we are getting H or not. If I take a closure of B, I am getting B, F, G, H. It means what? I can determine B can determine H here. So this is fine. Okay. So we can say B determine H is preserving here. Okay. So this is how you need to check for dependency preserving. Yeah. Yes.
Sir, what about the first three conditions? If we just use that, do we need to do this also?
First three condition is
For lossless decomposition,
yeah, that is
check
for
those conditions.
yeah, that is for lossless decomposition only. But if you want to check for dependency preserving, so this is a method we need to follow. That anyway you need to follow for decomposition here, lossless decomposition. Okay. So up to 3NF, decomposition is lossless as well as preserving. Okay. It's lossless and dependency preserving. But if you check for a BCNF here, there may be possibility that all the decomposition is in BCNF, but dependency is not preserved, right? So you need to check for those things as well. But up to 3NF, we can say when we decompose a relation up to 3NF, dependencies are generally preserved. Okay. So anyone, any question here? How to check for dependency preserving?
So you mean to say if the decomposed FDs are in 3NF, then we can say they are lossless and dependency preserving both.
Yeah. So if the decomposed relation is in 3NF, then we can say it is lossless as well as dependency preserving. So every decomposition must be lossless, right? And if it is in 3NF, then it must be dependency preserving. But in the case of BCNF, even if we decompose till BCNF, dependency may or may not be preserved, right? That we have to check. But once we decompose relation R to BCNF, sorry, 3NF, so we can ensure that already it's a decomposition is lossless as well as preserving, because anyway decomposition is should be lossless. Okay. So this is about a dependency preserving. So please try to watch the tutorials and solve the question based on dependency preserving. Do we have any question here? Yeah, so I guess this is a good question here we have. Let's discuss this particular question. Okay, tell me whether it is lossy or lossless. Anyway, answer is given here. But we have three functional dependencies, and you can see here we have this relation here. So bike name determine bike model. Bike model determine bike engine number. Bike engine number can determine bike name here. Is this decomposition is lossless? Yes, we can say. Which one is common attribute here? Because if I go with R1 union R2, are we getting all the attributes here? Yes.
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 R1 intersection R2, which is common attribute.
Bike model.
Bike model.
If I take a closure of bike model, which relation I am getting? R2, right? That is bike model and engine number here you can see. So we can say it's a lossless decomposition. So option B and D are eliminated. How to check for dependency of preserving here? Yes, same thing here as well. So here we have R which decompose into R1, that is BN BM, and here we have BE and BM. Okay, what is F1 here? Tell me. Yes.
BN determines BM.
And
BM determines BA.
can we write BM determine BN also?
Yes.
Yes.
What about F2?
BM
B
determines
determines
BM, which is already present. BM, but can we write BM determines BE?
yes, the second.
Yes.
Okay, no, BM determines B already present, but can we write BE determines BM?
Yes,
yes, transitive.
Because you can see this transitive dependency, so we can write it down. So BM determines BE as well. Now here we have F1 plus F1 plus. Let's take F dash equals to F1 plus union F2 plus. Okay. Now let's check for dependency preserving. Is bike name in and bike model is getting preserved?
Yes.
Yes. Is this getting preserved? Bike model, bike engine number, BMBE.
Yes.
Yes.
What about bike engine number, bike name, BEBN?
Yes.
Yes.
No, where we don't have
BEBM.
BEBN, where it is in this F1, F2,
Oh no.
right?
But
So
like from transitive we can,
yeah,
like from B to BM, BM to BN.
it means what we need to check for this FD, right? It is not directly applicable to F1 or R1 or R2, right? So for that, we need to take F dash such that F1 plus union F2 plus. Now you can see combining these four FDs. If I take a closure of BE, I will get BE, BM, but from BM, I'm going to get BN here. So I can see BE determine BN here, right? Now we can see dependency preserving. Anyone, any doubt here what we have done? Yes.
How can we say BM determines BN?
BM determines BN, right? This one.
Yes, sir.
Yeah. So here we just have two attributes. So we already know BN determines BM. So we want to check whether BM can determine BN or not. For that, simply take the closure of left hand side BM based on the parent functional dependencies. So whatever you're calculating here, right? F1 plus F2 plus based on the parent functional dependencies, can we write this like this? So if I take a closure of BM, what I'm going to get from BM here? You can see from BM, I'm going to get BE, right?
Yes,
But
sir. And
from
BE to BN, so transitivity.
BE to BN, right? So I can say BM determines BN also, right?
Yes, sir.
Yeah, like that. Okay. So always find out this functional dependencies based on the parent functional dependencies. And how we can do that? Simply take the closure of left hand side. So go with individual attribute of first here, like that. Okay. Okay. So yes.
Also, f dash is like the inverse of like if there is bn determines bm, so f dash will be bm determines bn.
No, F dash is simply we are taking combination of like all the at here, right? All the sets, all the elements of this particular set here, FDs from both the F1 plus F2. Okay. So in F dash, all four FDs will be there. This one, this one. And now we are checking whether this is applicable to this f dash or not, or we can derive this functional dependency from f dash or not. Okay.
Okay, sir.
Great. Yeah. So please watch tutorial, and we have few questions in grade assignment also. Please try to solve those questions. I hope this concept is clear now about decomposition and dependency preserving. Any doubt? Any question? Okay, great. So this thing we have in week 5. Okay, focus on this particular concept. Okay. Now in week 6, very important topic, we have normalization here. Can anyone tell me what is normalization? What is the purpose of normalization here?
To reduce redundancy.
Yes. So normalization means what? Decomposition of a table here. Like what we have discussed, how we are checking for decomposed relation here, or you can see where we have discussed that one, right? So here we have just checking for whether decomposition is lossy or lossless. But how we are going to get from here to here, that is what a normalization process is, right? I cannot store all the data into one table because that will be a redundant data here. Okay. So we need to store data in multiple tables, and how we can get a data back through foreign key. And foreign key is basically what a common attribute between two tables here, like that. Okay. So so how many normal forms we have? Yes, anyone? Normalization.
5.
1NF. Then we have second normal form, third normal form. Then we have BCNF. Then we have 4NF. We have 5NF as well, but we are not focusing on that. This is only important normalization form here. So how we can check whether our relation R is in one normal form or not, first normal form or not? Any condition for that?
Single value.
Atomic.
Atomic.
So there should be no multi-valued attribute. No multi-valued attribute, I am saying, that is MVA. Or we can say domain must be atomic, right? Atomic domain here. So what is MVA here? Yes, anyone, what is MVA? What is multi-val attribute here? How we represent this in AR diagram? By which symbol?
Two-headed, like right arrow.
Double ellipse, like that, right?
Yes.
So this is basically a multi-val attribute. And let's say, for example, phone number. So in particular column, we cannot store a two phone number like that because it's difficult to update or insert, right? So we don't do like that. There should be no multi-valued attribute. So we can say relation is in 1NF here. Okay. Simple one. What about 2NF?
No partial dependency.
No partial dependency. So what do you mean by partial dependency here?
Prime attribute determining non-prime attribute.
Prime attribute determining non-prime attribute. Is this correct?
Yes, sir.
Yes.
Really?
That
should not happen.
Non-prime attribute should not determine another non-prime attribute.
That is different thing here. What about this? Is this partial dependency?
Yes.
Okay, let's say for example we have a relation R here and A, B, C, D, and here we have candidate key is basically AB, and so A and B are prime attribute and C and D are non-prime attribute. Can I say AB determine D is a partial dependency?
No, sir.
No, sir.
No, then how this is applicable? This is also prime attribute, right?
Sir, basically left hand side becomes a super key, and that is allowed, but not for prime attributes.
Yes. So can we say a proper subset of candidate key determining a non-prime attribute, right?
Yes, sir. Yes.
Proper subset of candidate key determining non-prime attribute here. Basically prime attribute only, but this should not be a key. Okay. The thing is, this is also correct, but the only exceptional here is this attribute, prime attribute should not be a key itself. Okay, this is not allowed. Okay, this is basically a allowed in BCNF as well. So partial dependency means what? Proper subset of candidate key should not determine non-prime attribute here, right? So that is not allowed actually. Okay, so if I say B determine D, now we can say here we have a prime attribute. B is prime attribute, D is non-prime attribute. This is what partial dependency is, partially determining the attribute here, right? So here A and B is not fully, here A and B is a fully key, but partial key is determining this particular non-prime attribute. This is what partial dependency is, and this is not allowed in 2NF. Is this clear? This is also correct, but remember that prime attribute should not be a key. Only that's the required condition here. Okay. Is this correct? Is this fine about 2NF?
Yes.
Yes, sir.
What about 3NF?
Sir, once entire candidate key can map to this non-prime attribute, but any subset of that candidate key cannot map to non-prime.
Yes.
Okay.
A, B determine D is fine. B determine D or A determine D is not fine here. This is partial dependency. It's not partial dependency. Okay.
Okay.
What about 3NF?
No transitivity.
No transitive. So what do you mean by transitive dependency here? Someone said earlier. Yes.
Non-prime attribute determines non-prime attribute.
Yes. If non-prime attribute determines another non-prime attribute, this is not allowed in 3NF. This is transitive dependency, right? So first we need to find out candidate key, find out prime attribute, find out non-prime attribute, and check whether we are getting this functional dependency or not. If it is present, it means it is transitive dependency. Relation R is not in 3NF. Okay, so this transitive dependency here, we need to check for this. For partial, we need to check for this or this. Only the thing is, this should not be a key. What about BCNF? No, no, no. What about BCNF?
The A
Only
should be
candidate
super key.
key must determine, only the super key must determine the right.
So in the case of BCNF, all FDs left hand side must be a key here, right? So left hand side must be a key. So for all the functional dependencies to this relation of which is in BCNF, all left hand side must be a key here. So if I take a closure of any left hand side, that should give me all the attributes present in the relation R. Okay, that is what a BCNF is. Okay. What about 4NF?
No multi-value dependency.
No MVD here. Here it is MVA, that is attribute. Here we are talking about multi-value dependency. Now, what is multi-value dependency? Anyone?
So for a given relation, if we have the 4 attributes in them, and we see that we have 4 tuples in them, and we see the 2 of the tuples are all the tuples must match on alpha, and let's say T1, T2, T3, and T4 are the tuples. So I say that T1 alpha equal to T2 alpha equal to T3 alpha equal to T4 alpha, and the next condition is T1 beta should equal T3 beta, and T1 R minus beta should equal to T4 R minus beta. I mean the remaining attributes. And similarly for T2 and T3, it should be T2 beta minus R minus beta.
Yeah, so those 4 or 5 conditions we need to check, right?
Yes, yes.
But can I consider this one as T1, this one as T4, this one as T2, this one as T3? Then can we apply that?
Actually, it should follow whatever T1, T2, T3 we are taking.
In this particular sequence?
No, sir. Actually, T1, T2, T3, T4 has to be maintained.
So see, first you need to fix which we are referring to T1, T2, T3, T4. And throughout the calculation, you have to stick to that only, right? You can go in this manner or in any manner, but make sure that you should not change the sequence in between while doing the calculation.
Yes,
Okay.
sir.
So that is one of the way to remember all those four conditions. But other simplest thing is that, let me discuss it here. So the first thing is, for MVD to exist, there must be at least three attributes. At least three attributes must be present, right? If relation just have two attribute A, B, it means what? I don't need to check for any of this. If relation is having two attribute, this is already in 4NF. 4NF means what? It is in BCNF, it is in 3NF, 2NF, 1NF as well, right? Because it is in always higher normal form. So whenever any relation having just two attribute, no need to check. It is already in 4NF, BCNF, 3NF, every normal form it will satisfy. Why? Can you tell me the reason behind that?
Because it is not a multi-value dependence. It doesn't have a three attributes, so it just
Yeah.
have a two attributes.
So why is it in BCNF then?
One will always be super key.
Yes. So if you see here, only two possibilities are there. Either A can determine B or B can determine A, or both the things are possible. In any one of the case, left hand side will be always a super key, right?
Yes, sir.
So
Yes.
whenever a relation having just two attributes, that is already in 4NF. Okay, remember this one. So we don't need to check for those particular thing here. So MVD to exist, there must be at least three attributes. Out of these three attributes, two must be independent. So how we can define independent here? As anyone? It means what?
They should not imply each other.
It means what? If I say B determines C not exist, C determine B not exist, if both the things are there, it means B and C are independent here. Okay. B determines C also, C determine B also does not exist. It means we can say B and C are independent here. So at least three attributes must present and two must be independent. Then only we can say MVD will exist, right? So we need to check for that. So here we can say A multi determine B, and B and C are basically independent attribute. Okay, and then you can apply those four rules to check whether MVD exists or not. But what I am saying, you can simply check for this condition. If you want to check for A multi determine B, so see here what we need to do. Take any two tuple. Okay, take any two tuple such that A is same, means left hand side is same. Okay, because if you look at those four conditions, what we have defined, when T1 alpha equals to T2 alpha, then these four rules must follow, right? If you look at that particular slide, we have mentioned the first line, whenever T1 alpha equals to T2 alpha, then those 4-5 rules must follow. Okay, so whenever, if you want to check for any MVD, always take any two tuples such that left hand side is same. So alpha alpha must be same here, left hand side. Okay, now after taking those two tuples, what we need to do? Exchange the beta value. Exchange beta means what? B value here. Exchange a B value here. Okay, so let me take example here itself. So here we have A, B, C, and we are saying A determine B. Okay, so here we have A1, A1. So this is a required condition. Alpha must be same. Let's say here we have B1 and here we have a B2 here. Now take any two row such that left hand side is same. What we are saying, exchange the beta value here. Let's say here it is C1, this is C2. If I exchange the beta value here, this will become B2, this will become B1. It means what? You are going to get two new rows here. Can we say like that? That is basically A1, B2, C1 and A1, B1, C2. So we got two new rows here, right? A1, B1, C2. Now, if those two new rows are present inside your table, then we can say MVD exists. Otherwise, are not here. right? So if I just apply this here, I am getting two new rows, and this is what we are getting here: A1, B1, C1, A1, B2, C2, and these two new rows we got: A1, B2, C1, A1, B1, C2. Now, if I apply those four rules, alpha R1 of alpha beta minus alpha equals to R3 of beta minus alpha, then all rules will get satisfied here. Okay. If you can remember those things, you can remember that. But anyway, if you want to simply check whether MVD exists or not, simply take any two rows such that we have same left hand side value, exchange the B value, that is right hand side value, and you are going to get two new rows. If those rows are already present, then MVD exists. If those new rows are not present, it means MVD does not exist. Simple way to check the MVD exists or not. Anyone, any doubt here?
Sir, can you please go to that slide?
Yeah.
Done, sir.
Yeah. So I think in the slide, let me take the slide. We'll verify this one, whatever I'm saying. EPM. Okay. Is this visible? This slide?
Yes,
sir.
sir.
So you can see here, either you can go with this one, but what we have discussed. This is my A, this is my B here. Take any two left hand side row such that alpha value is same. So let's go with this AHA and this AHA, or this one or this one. Okay. So let's, for example, let's go with this one and this one, such that we need to exchange the beta value. So beta value must be different here. So here we have AHA, and this is Silverstack, and this is Netherpelt. Now what we have said after that, exchange the beta value. Okay. Just a minute. Okay. So this will become what? Netherpelt, and this will become what? Silverstack. Now we got two new rows. AHA, Netherpelt, John D. Is this present in the table?
Yes, sir. It's
This
present.
one only, right?
Yes.
And what about an AHA, Silverstack, John D? Already it is present, right?
Yes.
So we can say, or even if you take these two rows, let's go for this one, right? So AHA will exchange. Here it will become Netherpelt, it will become Silverstack. Now AHA, Netherpelt, John D is present. Yes.
Yes.
AHA, Silverstack, William W is present. William M is present. Yes. Right. Same go with this two. So whatever we have discussed, right? Take any two row having same alpha value. So that should be applicable for all the unique alpha value. So whatever the unique alpha value we have to check for all this case. Once we satisfied for AHA, we don't need to check. Then go for OSO. Okay. So whatever the unique alpha value we have in that particular, for that we have to check. So if I go with OSO, here we just have two rows here. Can you tell me? SS. So anyway, we are going to get same rows here, right?
Yes.
So MVD exists here. We can see. So this is how you can check here, right? Even you can see course determine a book. It means what? Course can determine a lecture as well. This is what we can say. And same thing you can apply it here as well. So for this table, MVD exists, we can say. What if I just remove this particular row? Will whether MVD exist?
No.
No, sir.
No. Because for AHA, this will get satisfied. But for OSO, this will not get satisfied, right? So what we have said in R such that T1 alpha must be equal to T2 alpha here. So if I just remove this row, then MVD will not exist, even if it is satisfying for AHA here. Okay. Okay. Anyone, any doubt? Sorry. About MVD? Okay. Anyone solve this question? Anyone attempted this particular question? Okay. So See here we have this A, B, C, D, E following MVD, right? And our tuples consist of these two rows, right? So which of the following tuple must be in R here? So let's try to solve this question. Here we have R. So A, B, C, D, E. Okay. So 0, 1, 2, 3, 4, 0, 5, 6, 7, 8. So we have just two rows, right? Now we know that MVD A multi determine B exists. Now what we can do about this? Yes, anyone? How to proceed? Whatever we have discussed it here, can we apply that here?
We can interchange and make two new rows.
So I'm going to interchange the B here because keeping the A same. If I interchange this one become 5, this will become 1. I got two new rows 0, 5, 2, 3, 4, 0, 1, 6, 7, 8, right? So these two rows must be present inside the table. Then only this MVD will exist, right? So you can see one of the option is basically this one, right? So this is basically a correct here. 0, 1, 2, 7, 8, no, 0, 1, 6, 3, or no, right? But we have just checked for this one. What about this one? What to do now? How to check for B determine D?
Exchange D values.
Exchange D values, keeping B values same, right?
Yes.
Yes, sir.
But here we have two B values, na? 1 and 5. How to proceed then?
Then like for 1 we'll exchange the 3, 7 and then we'll do it again for 5.
Okay, great. So here 1, 0, 1, 2, 3, 4, and here again 0, 1, 6, 7, 8. So here we are keeping B same, B multi determine D. And then in the next scenario, I will keep 5 same. So 0, 5, 6, 7, 8, 0, 5, 2, 3, 4. Right? Now see, keep like left hand value must be same here. So B is same and D is what we need to interchange. So A, B, C, D. So here 3 will become 7, 7 will become 3. So 1, 2, 7, 4, 0, 1, 6, 3, 8. This is correct, right?
Yes, sir.
And here also we need to replace this one. So 0, 5, 6, 3, 8, 0, 5, 2, 7, 4. We just interchange the beta value here. Beta is basically D here. Now, if you observe, these 4 rows is basically and this 4 rows. So in total, we are going to get how many rows to satisfy both the dependencies?
12.
8 rows. Now, these two are duplicate only, right? So total 8 rows we are going to get to satisfy both the MVDs. And out of these 8 rows, we can ask any one of the rows in this particular options here. So option C and B, you can see 0, 1, 6, 7, 8 is basically this one. 0, 5, 6, 3, 8 is basically this one, right? So 0, 1, 6, 3, 4 not present, 1, 2, 7, 8 not present, right? Out of this, the 2 rows, we can also add any one of the rows, so that will become another option. Anyone, any doubt what we have done here?
Sir, in the second part, when we
yes, second part.
When B determines D.
Please mute.
Sir, the thing is, I'm not able to get this the table. How did we create the 0, 1, 2, 3, 4?
Okay, this part you understood about the A
Yes,
multi-determine B.
Yes, yes.
Yeah. So once we got this one, this is this we got for what A multi-determine B, right? For this particular function MVD. But this is also present, right? So we need to apply this as well.
Correct.
So for this, what we have said, left hand side must be same, right? 2 alpha values, T1 alpha equals to T2 alpha. But if you observe here, we have 2 unique beta values, sorry, B value here.
Yes.
So for that, we need to take for both the beta thing here, for both the B case here. That's why we have taken first 2 rows for B equals to 1 and then next 2 rows for B equals to 5. And then we have applied this particular MVD here again. Okay. Or even you can take this table and be multi-determine D. So first take this T1 and this T2 interchange the D value here. It will be 7, it will be a 3. Write down those 2 new rows and then take this T1 and then they take this T2. Again, interchange the D value, write down those 2 new rows. Same thing here. Okay?
Sir, what was the reason for taking B value different? Because what we do is we take the value of D.
No, here left hand side is basically B attribute for this
Yes,
particular
yes,
case, right?
yes,
So what we are saying, whenever T1 alpha equals to T2 alpha, so alpha
yes,
is basically alpha determine beta, right?
yes.
So left hand side value, then only we can exchange the beta value here. So that's why we take 2 rows such that left hand side value is same. So here we have 2 unique values in the case of B because 1 and 5 is present.
So
For
because
both
we
the
didn't
case,
have that alpha value, so we have created a new tuple for that.
no, we are not created. So we got this table, right, from first MVD. Now,
Yes, sir.
in order to verify this particular MVD, what we have said, take any 2 rows such that B is same, alpha value is same. So we can take these 2 rows, right, or either these 2 rows, anyone, right, anyone combination first.
Okay,
if,
okay.
if you want to verify whether MVD exists or not, so take any 2 tuples such that left hand side value is same. So I want to verify this one first, right, because already applicable. So I will take any 2 rows such that left hand side value is same. But I can take this 2 or this 2, right? First I will take this particular 2 rows here. Then after that, exchange beta value here. Beta value is for this particular combination 3 and 7. So we'll exchange that and we
Yes.
will get 2 new rows. So that we have written it here. Now, but we have one more value for B. So go for that value as well. So whenever this 2 rows will be same, left hand side, then again exchange the beta value and again we are going to get 2 new rows here. Like that.
Yes, I got it.
Okay. So please try to solve this question again. Okay. So just remember this thing. Take any 2 tuples such that left hand side value is same. Exchange beta value and 2 new rows we are going to get. If those rows are present, MVD exists. If MVD already exists, it means those 2 rows must be present. That is what we have applied it here. Okay.
Excuse me, sir.
Yes.
Sir, in this question, so how many rows we need to, how many tuples we need to add to make it MVD?
So here we have given 2 tuples. So total 8 tuples are required here, right? So 6 tuples we have to add. 2 for this one and 2 for this one, 2 for this one.
Okay, so sir, is there any formula, to, have the value, final value,
No. For
minimum
number of
value of
tuples, no, we don't have any
Mhm.
formula. Okay. For MVD.
Okay.
Okay. This is about MVD, and let's discuss one question on normal forms here. BCNF left hand side value must be same. So simple question. Any difficult question? Here we have. Okay, great. So here we have question number 10, right? So we have R, we have F. Now first we need to check whether R is in BCNF or R is decomposed into 3NF, BCNF. Which one of the statements are correct, right? So you need to check for each one of the statement is MSQ question here, right? So can we decompose this relation R to a BCNF? Let's try to do that. How we can decompose a relation R? So up till now we have just checked how to check whether a decomposition is lossy or lossless, or if decomposition is given, how to check whether it is normal form or not. But what if we have given the R? Now we need to decompose this to BCNF. How to do that? First, tell me.
We have to take 2 tables, alpha union beta and r minus beta minus alpha. So then we have to check again on BCNF on those tables.
Okay, so what is alpha? What is beta here?
2 relations.
Okay. Yeah, so how we are going to determine that alpha and beta two relations here? So I need to decompose this to be CNF, right? For that, it should be in 3NF. For this, it should be in 2NF. For this should be in 1NF. So here they have not mentioned, but we assume that all relations are in 1NF. Okay, unless we specify in the question that this relation is having multiple attribute, always assume that relation is in 1NF. Okay. Now it is in 1NF. Now is this in 2NF? Can you check for 2NF? This relation R is in 2NF.
We'll have to find candidate keys.
So what is candidate key here? P and Q and O all are present. Then
One of them is NM.
yeah, so in that case, you can go for M, take a closure of M. We are going to get all the attributes here. So M is basically candidate key. And go for N. From N, we are not going to get anything from N.
Q is there.
Yeah, Q is there. Now we have done with M and Q. Now we left with NOP. So go for combination of NO, NP, or OP. You can find out OP and ON is basically a candidate key here, right? So already it is written here, so I'm directly writing it down. But I hope everyone understand how to find out candidate key, right?
Yes, sir.
Now we have prime attribute. What is prime attribute here? M, Q, O, P, N. All are prime attribute here, right?
Yes.
Okay. So is this in 2NF? Now check.
Yes.
Yes, because there are
There's
no
non-prime.
No non-prime attribute, right? So this is in 2NF, right? So here you can see, even though it's a subset of candidate key, but P is basically prime attribute here, right? So that is fine. So it is in 2NF. What about 3NF?
Yes, because everything on RHS is a prime attribute.
Yeah. So it is in 3NF also. Now check for BCNF. So it is in BCNF. Left hand side must be a key for all the FDs. So is N is a key?
No.
No, sir.
Q is a key?
Yes.
Yes.
No.
This
Yes.
is fine. OP is a key?
Yes.
M is a key?
Yes.
Yes.
So these three are fines. These three basically are fine. What about N determine P? This is violating my BCNF condition. It means what? R is not in 3NF. Now, can we decompose this R to BCNF and then check whether it is in dependency preserved or cannot be preserved? That is what we need to check. So it is in 3NF, we already know, right?
Sir, can you repeat how it is not in BNF?
Yeah. So the condition for BCNF is basically left hand side of every functional dependency must be a key. So you can see N is not a key here. This is violating my BCNF condition. Q determine M, yes, because Q is a key. So this is fine. OP determine Q, yes, OP is key. This is fine. M determine NO,
Yes,
M
sir,
is
yes,
basically
sir.
key. This is fine. Only this is violating my condition here. So how to decompose now? Yes, anyone?
NP in one relation and others are separate.
Yes. So
Yeah,
check
M
which
and
of
OQ.
okay. So check which functional dependency is violating that particular normal form. So in this case, NP is violating. So take the closure of left hand side here. What is this closure here? NP. Any other attribute?
Nothing.
No.
No. And make this as my R1. So we are decomposing this R into R1 and R2. So this is basically my R1 is
Excuse me,
basically.
sir.
Huh? Yes.
Sir, why is N not in candidate key?
Because if you take the closure of N, we are not getting all the attributes here. So N is not a candidate key here, right? If you take the closure of M, Q, then OP and ON, we are going to get all the attributes in the relation R here.
Okay, sir.
Yeah. So here this FD is violating my functional dependency. So what we are doing, we are taking closure of n. We are finding it out how many attributes are there. Now we are naming this as R1. So my R1 is NP here. What should be my R2? Now for this attribute for R2, you have to remember those three conditions. Okay, what we have discussed for decomposition here. This is applicable here, right? So while decomposing table, we don't decompose R directly into R1, R2, R3, R4, R5. No. First we decompose into R1 into R2. Then we check R1, R2. Then we decompose R1 into again R3, R4 like that. Okay. So here at a time we only decompose relation R into two tables here. So first, if I know my R1 is NP, I want lossless decomposition. What attribute should be there in R2? Tell me now.
MNOQ.
Meaning
MNOQ and then one
plus n.
common attribute.
Yes, n is common.
M and OQ because we have to cover all the attributes here, right? So you can
Yes,
see
sir.
M and OQ. Now we need to find out the common attributes such that it should give me either R1 or R2 based on second and third condition. So which should I add N or P here? Okay, already N
And
added.
N
N
is
is already
already.
there.
Sorry. First I will write MOQ. So this is better. Now we need to add either N or either P. So if I add P here, but if I take a closure of P, I am not getting R1 or R2, right? So we need to add N here to get R1 intersection R2 N. So we have common attribute because N is basically key of R1. So we can now join this table to get my relation R back. Is this clear? Any question till now? How we got R2? Hello.
Clear, sir.
Yes.
Okay. Now write down the FD F1 N determine P. What about this R2? F2 will be what? Q determine M. OP नहीं है इसमें P नहीं है. M determine NO. Right? So what about this FD here? Where we can write this? Because P is not present in R2, right?
Yes.
So we need to check whether this is preserved or not. So again go by that particular method. Find out F1 plus F2 plus. Take F dash equals to F1 union plus F2 union here. So N determine P, P determine N, no. You can see Q determine M, M determine N, O. So I already know that Q is basically key here, right? M is basically key here. So can I say if Q determine M, Q can also determine O and Q?
Yes.
M can determine N, O, M can also determine Q, right? So we are done with M and Q, and the combination is basically O N. So O N can determine nothing. That's it. So we got this one. So here we got F1 and F1 plus. Now,
Sir, in F2, how did we conclude that M determines Q?
because M is basically key, right? So if I take a closure of M here, I'm going to get all the attributes, right? So it means what
Sir,
M
in
can determine.
F2, it is not because we are not having that one FD.
No. Here we are finding out F2 closure, F2
Yes.
plus. So in
Yes.
this case, we need to take the parent functional dependencies to find out the
Okay. Yes.
applicable functional dependencies. So we use parent functional dependencies, but we write down only those FDs which are part of that relation here. Only those attribute only. Okay. M can also find out P here, but we are not written M determine P because it is not part of R2. So even if you take F1 plus union F2 plus, still you are not going to get OP determine Q here, because if I take the closure of OP here, that's it. I'm going to get OP only, not Q. So OP is not preserved here. So that's why option D is correct, cannot be preserved. Okay. So this is how you can solve this question. Okay. This will take time. Okay. This question is difficult one because you need to decompose, then you need to check again is preserved or not, like that. Okay. It's not a straightforward question. You need to do a little bit of work on this. Anyone, any doubt in this question? What we have discussed?
Sir, in the F2 closure, how Q is determining OQ?
how Q is determining O, not Q. M
No,
and
it's
O.
ON.
O N. Yeah, N is remaining,
Yeah.
right? And so what we said, whenever you are finding out the closure of attribute, right? Take a closure of Q based on the parent functional dependency. So Q can determine M. From M, it can determine NO, and N can determine P. It means what? Q can determine M, N, O, P. We can write like this. So whatever the attribute is applicable here, so Q can determine M as well, O and N as well. Okay. By decomposition rule, Q can determine M, Q can determine N, Q can determine O, Q can determine P. Like that we can write, right? If we have this FD. Is this okay?
Sir,
Huh?
sir, I am not clear on the deep composition part.
Which one? Decomposition.
Decomposing, yes.
Okay, so first, like our aim is to decompose into BCNF, right? So first it should be in 1NF. So already we assume it is 1NF. Check for 2NF. Already we have all the attributes of prime attribute. We don't have any non-prime attribute. So in that case, we'll R is basically in 2NF as well. Then for 3NF also, here we can see we don't have any non-prime attribute. It is in 3NF. And let's say, for example, we have non-prime attribute, let's say P here. In that case, N determine P will violate my partial dependency 2NF, right? So in that case, we need to decompose the table for 2NF. But here it's not that required. Okay. So we can directly see it is in 3NF because there is no NPA determine NPA here. Now we have to check for BCNF. The condition for BCNF is left hand side must be a key for every functional dependencies. Now we can see here Q is basically a key, so this is fine. OP is basically key, this is fine. M is key, fine, but N is not a key here, right? So this is violating my BCNF condition. It means what? I need to decompose the relation now. Now, while decomposing, I need to take a FD which is violating my BCNF condition. So if I take this functional dependencies or whatever the FD it is violating, take those and simply take the closure of left hand side attribute. Whatever you are getting in left hand side, in this case we are getting NP here, so that will be one of my table. Let's say for example R1. Okay, now we know R1 is basically NP here, but what about R2? Because we are decomposing R in R1, R2. So for that purpose we are discussing this tools. Hello. Yeah. So we know R1, so what attribute should be part of R2? So based on these three rules, you can see first all the columns must be present. So remaining column is MOQ. So we have done with the first condition. Second condition is what? There must be a common attribute. And that common attribute must be a part of any one of the relation as a key. So you can see here, we can add N or P, but we cannot add P because P is not any a key of R1. So we need to add N here. This is basically a R2 here. And then we are checking for a dependency preserving. Now is this clear for a decomposition?
Yes, sir.
Yeah. Okay. So in while solving the questions, don't just simply go through the conditions here. Try to decompose that particular table. Okay. So in this way, you can understand the concept in a better way. Okay, so here we can say satisfied by the R. So anyway, check every FD is a left hand side or not. That's it. Okay. Okay, so this is about normalization concept here. Anyone any doubt in normalization or 4NF form? So let's quickly discuss remaining questions of week 5, week 6 here. So BCNF condition, right? Left hand side must be a key of every functional dependency. If ABC is a key, yes. AD is a key, yes. So this is applicable. For this AB is a key, can you check? A, B, C, D, yes. CD is a key, no. This is also no. So violating the BCNF condition, right? Again, this is same manner here. So similar question you can solve. So here we solve all the questions from week 5, week 6. Okay, let's try to solve this question. We have a database engine designer. Observe that relation R is in 2NF. Okay, it means what? No partial dependency and has transitive functional dependencies. Relation R is decomposed into R1, R2 such that decompose is in 3NF. So we have R which is in 2NF but not in 3NF. Can we say like this?
Yes.
Because of this statement given to us, now we are decomposing R into R1 and R2 such that it is in 3NF and lossless. So this is in 3NF. Now the designer observed that R2 is in 3NF but not in BCNF. So relation R2 is further decomposed into R3, R4, right? Such that a decomposition is in BCNF. Now this is in BCNF. It satisfies the following condition. So R2, R3 union R4, yes. R3 intersection R4 determines R3, yes. So it means we can join to get the original relation back. A decomposition of R2 into R3 and R4 is lossy. No, it's a lossless decomposition. R1, yeah. Anyway, simple question here, right? This is not correct here. Okay, anyone, any doubt here in this particular question or any doubt in week 5, week 6? So please focus. Yeah, you can see one of the question can be based on the SQL from the previous week 1 to 4. Okay, there is a possibility one of the question can be there, but most of the questions from week 5 to 8 only, and focus will be more on week 5 and 6. So this we have solved. Yeah, here we have canonical cover here. Okay, what is canonical cover? Yes, anyone? We can say canonical cover is basically a minimal cover as well. Okay, so
It is a minimal dependencies, which, like, if we take, like, if it's FC, the closure of FC would be same as the closure of the original F we get.
yes, it means what? F and F's are equivalent, right? This is what we can say, are equivalent. So we can say that okay, from F we can determine FC, and from FC we can determine F. So that is basically F covers FC and FC covers F. Then we can say F and FC are equivalent here if both the conditions are satisfied. Covers means what? If I'm able to determine all the FDs of FC using F and all the functional dependencies of F using FC, then we can say it is equivalent here. Now just check the options here. That's it. So here L determines Mn. So first what we are going to do, take this as F, this is as FC. So can we determine all the attributes of FC using F? Can we determine L, Mn? Already present.
Yes, sir.
What about this? Already present.
Yes.
KMI is present.
Yeah, it's present. The last one.
Yeah. KM determine I, KM determine En. Yes. What about KM determine N? Is this present? Yes.
Yes, sir.
So F covers FC, but whether FC covers F, that we need to check now. Now, can we determine IK, determine N using option number A?
No, sir, it's not possible.
Just take the closure of IK based on FC. So IK, that's it, I guess, right? Yeah. So we cannot determine this FD. It means what? FC cannot determine F. So option A is not correct. Now, in this way, you need to go for each and every options here. So L, M, and determine JKL. Same we have discussed. IKN is, can we, yeah, already present here. KNJ, yeah, you can see KNJ here. So see here, KN determines JL. So by decomposition rule, we can write KN determine J and KN determine L. This is via decomposition rule. By union rule, we can write like this: Kn determine Jl. We can only decompose or apply union rule to the right hand side. I cannot write like this: K determine JL or N determine JL. No, you cannot decompose left hand side. You can decompose right hand side. Okay, so this is what decomposition or union rule is. So Kn determine J, yes. Now from option number B, can we determine F? Let's see. IKN already present. LMN already present. JKL already present. KNJL. KNJ is present. KNI we have to check. KNL we have to check. Okay. Now we will get Kn determine L using option number C. Can we check? Are we getting L if I take a closure of Kn here based on option number B?
Yes, sir.
Yes.
Kn
Yes.
gives J and Jk gives L.
Yes. So we are getting this one. IKJ don't have direct here. So again, take the closure of IKJ and can we get
Yes, sir.
J here?
Ik gives N and Kn gives J.
Yeah. KMIJ. So KMI is there. If I take a closure of KMI, IKN. So again, satisfied, right? So in this way, we need to check for each and every options, and both the things should get covered to get to be an equivalent. Okay. This is how we can check equivalence of FD here. Anyone, any doubt here? You can check for option number C and D. A simple question here. Okay, so we have discussed. So remaining questions are from week 7, week 8. In weeks from week 7 only, you can see that Python DB connectivity, that part, or you can see this type of question, right? Where it is? Yeah, this one, right? So here you can see this type of questions you can expect, or MRU, LRU, those thing. And from week 8, we have a binary search tree and magnetic disk. These three important topics you can focus from week 7 to week 8. We'll be discussing in tomorrow's session, week 7 and week 8. Anyway, any doubt in week 5 and week 6, you can ask now. Any previous year question, if you're not able to solve, you can ask. Okay, any doubt from week 5, week 6, any previous year question, assignment questions, any question? Okay, that's it from my side. Then, thank you. Thanks for joining, and
Thank
all
you,
the
sir.
best for
Thank you,
quiz
sir.
too. Yeah.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Chalo, good night.